Hello, how you doing? Hi, Sackville. Good to see you again. Happy holidays. We've still got a whole week left, which is rather nice, isn't it? Something to enjoy. The weather's not been too disgusting neither, so I hope you're doing well. I hope you had a chance to unwind a little bit. Just thinking back to last week and sort of the main push there was thinking about this mark scheme. So the eight marker: legal, ethical, environmental, and cultural, and privacy, and just thinking about the importance of A, being thorough and giving yourself some thinking time, and then B, trying to get into that top band by making sure that you argue both sides really well, by thinking about pros and cons, for example, thinking about the stakeholders as a way of getting in there, and then referring whatever you're saying back to the context of the question. And those really are your your key things there. I think 1 week's never quite enough to really give it for that. So I hope that was enough. So today, we're going to look at computational thinking. So let's jump straight in. And this is really a relatively I think a relatively easy one conceptually, because this is the start of paper 2 now. We've done paper 1, we've done the things stuff, plus that weird one at the end about the legal and so on. And now we're getting into this idea of how it is you actually produce an algorithm. How do you make an algorithm? How do you write a program? How can you write a program so that you can keep the software safe and maintainability, that sort of thing. So we'll jump in and have a look at this. I've got a question for you. I'm not sure we've currently got anyone here. So actually, I'm not going to run through these quiz questions. I'll see if anyone joins that a bit later on. Okay, so what I'll do, I'll jump straight through, because rather than doing quiz questions for the world not here, I'll just get on and go from here. What's it all about? Right, so we are looking at 2.11, which is computational thinking, and that focuses on abstraction, decomposition, and algorithmic thinking. So that's really the topic we're looking at today. And what you need to know is how these principles are used and how they can be used to refine and define problems. And I think thinking about different situations in which they may be used, and we'll do a little bit of that today, jumping in and looking at, I think, the most obvious example of abstraction. I always think decomposition is a bit easier, but abstraction is more difficult to actually sort of describe, really. So we're in computational thinking 2.11. So the main idea with computational thinking is that you're going to take a complex problem and you're going to try to understand it, and you're going to develop solutions for it. So whenever anyone writes software, you are actually trying to solve a given problem, all right? And the key principles around problem solving, and it's no different when you're writing a software, a computer program, is that abstraction, decomposition, and algorithmic thinking are the key areas that you're going to sort of use first of all to try to get to understand the problem and how you might solve it using a computer. So let's start with the idea of abstraction. Essentially, when you abstract things, you're ignoring the characteristics of the problem that won't help you solve it. So if it's not important to understand something, we're going to look elsewhere. And what you do instead is you focus on the characteristics that will help us solve the problem. Well, that's all well and good, but it's a bit wishy-washy, isn't it? So let's go into a little bit more detail on this. Abstraction means identifying only the necessary information that you need to solve the problem. What do I have to know to solve this problem is a really good way of thinking about this. Anything else you ignore because it's not going to help you solve the problem. So you've got that sort of rather ridiculous graphic at the bottom there. And of course on the right hand side, the square, that's complete abstraction. There's the heart, which is the standard sort of, image you might see of a heart, like a sort of cartoon. And then you've got too realistic, which you don't need on the left-hand side. So we're looking for that middle spot, something that's going to help us solve a problem. Right, enough waffle. Let's have a look at this example here. And I think this is useful. So this is the London Underground map. You won't recognise it because this is the accurate London Underground map. So this is where all the stops actually are. And you can see that the original map is in fact laid out over a map. And this is accurate, far more accurate than the one that we actually know and love and use. And I'm assuming here that you've been on the Underground. You'll certainly recognise what a London Underground map looks like. So here you can see that you've got lots and lots and lots and lots of detail. But the question is, do we need it? And of course, we're thinking about abstraction here. And then we've got item 2. And this is the 1933 Harry Beck map. He was an employee of London Underground. He produced this map, and when he showed it to the management, they didn't like it. They thought it was just too crazy, and people couldn't possibly understand that. It was just too futuristic. It was too strange, all these straight lines. But of course, the process that Harry Beck went through to produce this map is perhaps the single best example of abstraction in practice, because you can see that while a lot of the accuracy has been lost, it's not at the expense of it being an easy-to-use map. In fact, this map is far more simple to use because it simply has the information that you need and nothing else. Okay, these two maps side by side, one accurate, one inaccurate. But let's have a look at how the second map, the Harry Beck map, has used abstraction and how that's been incredibly useful. So first of all, thinking about the original map, green spaces. Are there any green spaces? No. But do we need green spaces? No, we don't. What about roads? Well, if you're underground, look, you don't need roads. So all these sort of roads that you can see on the map, the A3, the A215, they're just not necessary. Road names, road places, borough names, again, all of them on the map on the left, but not on the map on the right, because you don't need to know that when you're on a train. The accurate flow of the Thames? No. It's helpful to know whether you're north or south of the river when you're in London, but you don't need to know exactly how the Thames is flowing. And what about, lastly, the distances between stops? If you look at the map on the left here, for example, let's think about over here. I'm going from Wood Lane. In fact, I'm on a. Let's actually go to a tube line. Here we go. Shepherd's Bush. Let's start Shepherd's Bush and go up to Willesden Junction, and you can see that is a heck of a long way. But look at all of these distances here. Okay, they're all really, really small. And that's because it doesn't matter. If you're on a train, whether it takes 20 minutes or 5 minutes to get between stations, it doesn't matter. You just need to know which station is the next one and which is the terminus. That's all you have to worry about. So that's why this map was such a sort of good example of abstraction. Right. Let's see if we can get on. There we go. Right, so I think we've made the point there. Now, secondly, we move on to decomposition. Now, decomposition is a question of breaking down a complex problem into smaller parts, and these smaller parts are more simple to solve than the whole thing put together, because you've broken it down until you've got one problem that you need to solve. And if you can do that for all of your issues, then that makes the problem easier to solve. So the smaller problems can be solved individually and can be solved in a simpler way. I mean, here's a really obvious example. If you think about a classic French kitchen, where they're sort of making starters, main course, and they're making dessert. Well, you can see that the way they have it broken down with different sections for different dishes, and for a chef and a sous chef working together, you can see how you can already, this is another example of decomposition, or a really good example of decomposition, is that this has been broken down until you're down to someone's making mashed potatoes, someone's making the other vegetables, someone's making the meat, and so on. So you've actually broken it down into much smaller problems, which you can then solve. And of course, that is how sort of the idea of the French kitchen came about, is because they simply looked at all of the jobs that you had to do and then worked their way backwards. So they actually worked it out using the opposite of decomposition, which is really interesting thought. So that's a really good example of how decomposition is used in everyday life. Now, algorithmic thinking, which is the third area we're going to focus on today. First of all, what is an algorithm? An algorithm is a sequence of clear instructions. And computers, we know, are very simple creatures. They are, well, they're on-off switches, aren't they? So therefore, all a computer needs is a simple set of instructions that it can follow, and it's used to solve a problem in a step-by-step manner. For this to work, the algorithm has to be unambiguous. In other words, it has to be clear. There can be no ambiguity. There can be no confusion about it. It needs to be absolutely simple and plainly clear. It also needs to be complete. There has to be a start, a middle, and an end, and it has to work. In other words, it has to be accurate. And it needs to be consistent, so it's got to give you the same results every time that you run it. Something that gives you results 9 times out of 10 is not going to be a consistent program for you. And it also has to be efficient. And in this case, we're thinking about an efficient use of memory. All right, so let's push on and have a look at the next one, thinking computationally. Now, computational thinking is not the same thing as programming. In some ways, it has something to do with programming because it's something that you might do after you've done your computational thinking. But the computational thinking is your first step before you even think about trying to create something in a high-level programming language. So programming instructs the computer what to do and how to do it. And using computational thinking, it helps you work out exactly what you want to tell the computer to do. So this is the process where you're breaking it down from a human problem in human words into a set of simple steps that a computer can actually follow. Thinking about brushing your teeth, it's also got many subtasks. You need toothbrush, you need toothpaste, you need a sink and water, obviously. And you've got to put the toothpaste on the toothbrush, well, you know how to brush your teeth. But you can see that even though that's such a simple activity, it actually is, it involves a huge number of steps. And if you miss one step out, it all goes wrong. You probably did miss several steps out when you were first being shown how to do it, like dropping your toothbrush on the floor. That's something you don't do very often. But you can see that even something as simple as that can very quickly get out of hand in terms of how many steps are actually required and how accurate they need to be. Okay, so I think this one's fairly obvious. We talked about abstraction. Is it the process of adding detail to a problem to better understand it? No, it of course isn't. Decomposition is breaking something down into smaller parts. The tube map is a brilliant example of abstraction. And the game FIFA is not written as one gigantic, huge program. It's written as several modules. And of course, that's another example, modularization of breaking a program down into smaller parts, into smaller sub-programs, because they're easier to manage. And this is also an allegory thinking about the layer system, where you've got thinking about networking and the different networking tasks that are taking place and the way that they've been arranged as a series of layers, because they are complete and they only talk to the layer above and below them. So it makes it much easier to work on and improve that layer. So that architecture is really interesting, and it kind of runs out to this as well. 3.5, without RAM, a computer would run slowly. Well, if you think about what RAM is, and they will ask you that in the exam, RAM holds all the data and instructions currently in use. So yeah, if you haven't got RAM, you've got no computing. You haven't got nothing at all. 3.5 gigahertz, 3.5 billion, not million, fetch, dig, and execute cycles a second. And when you switch a computer on, it's not the OS that takes over straight away. It is, of course, the ROM chip and the bootstrap program that gets it started. And then eventually, once it figures out that it's got an environment in which it can run Windows or Linux or Mac OS X, whatever it is, it will then take the operating system from the hard drive from secondary storage and load it into primary storage, i.e. RAM. It's amazing how many people still struggle with that story, but it's so important. It's so helpful to know that. And yes, making a processor involves creating silicon from sand and then turning it into an ingot and slicing it into wafers. Thankfully, that's way beyond what's required for this course. And of course, the fewer lines of code you write, yes, the better the better that code is, or it's a good example of that because the code is more efficient. Okay, so we're now into quiz time, but I don't actually have any quiz competitors here, so I'll just run through a few of these. I'll put a few of these up just to get us started. See if you can get an answer in for that one. I'll just give you 20 seconds when you're at home. Okay, so This is one of the ones from a past paper question. DBAF is the answer. So decomposition, that's breaking a complex problem down to smaller parts. We've covered that one a few minutes ago. Abstraction B is hiding or removing irrelevant details. Input sanitization A, that's cleaning up data. That one we haven't covered today, but that could well be in there. And casting is converting one data type to another, for example, an integer to a real number. Okay. Let's try this one. Which of the following is not done by abstraction? And the answer is, of course, breaking down the problem into smaller tasks. Let's try one more. Decomposition allows each task to become, is it A, more manageable? Is it B, quicker? Or is it C, easier? I'll just give you 20 seconds on that. Okay, and the answer is 40, slide 42. The answer is more manageable. Okay, well, I think that's been an incredibly short session this time because we've not really had anyone to answer any of the quiz questions. So I think that I will stop there today and we can crack on with the next topic next week. Okay, cheerio, bye-bye.